AP. Today's section is on 1.5. It's on infinite limits. Again, I encourage you always to read your textbook section to get better understanding of the content. Our learning targets today are: I can determine an infinite limit from left and from the right. I can find and sketch vertical asymptotes of graphs of functions. So, difference between this section and the last is we're dealing with the relationship of vertical asymptotes with limits, and we're dealing with infinite limits as well. Okay, first of all, an infinite limit is a limit in which f of x either increases or decreases without bound as x approaches c, a value. Either the limit of f of x as x approaches some value is going to reach positive infinity, or it could reach negative infinity. So, quick example. On this one, here is our problem. We are going to find the limit of 1 divided by x plus 1 as x approaches negative 1. Please notice there's no plus or minus sign here, so it is a two-sided limit that we're dealing with in this problem. The question says model numerically and graphically the following. So if this is our question, here's my direction. I've got to do this two different ways. The first thing I chose to do is take the expression part of the limit, write it over here to the side, and look at it as an equation. So that way when we got to the graphing part and even the numeric part, which is the table, we could kind of connect the two. So quick reminder of numerical, we're doing a table figure. It does say to the x has to approach negative 1. You notice in my table I put negative 1 there. Also with a direct substitution, if I put negative 1 in for x, that would be 1 divided by 0, and obviously that's undefined. And so that's the reason we're trying to figure out what the values are going to do below negative 1 and what's going to happen to the y values when x is above negative 1. And so you're going to choose numbers that are relatively close, like we've done in the past. So you're going to take, I just chose negative 1.11. You could have said negative 1.01. So that's your choice. And you're going to substitute it back up here into x value in the calculator. So it's going to be 1 divided by the quantity negative 1.11 plus 1. Okay, you're going to record that here. And let me do that one more time. Yeah, and I just ended up getting negative 9.0909. And so, like, remember my comment from the past, when you are using or rounding decimals, always make sure you give me 4 numbers after the decimal in calculus. Then we're going to move over here and try negative 0.99. Put that value in place of x. And I got 100 there. Okay, now I'm going to do the negative 0.9. Oh, I should switch these. Sorry about that. So we're going to take care of that mistake quickly. Okay, so this one was this one's 10, and this one's going to be 100. And so you can see with the question that I've given you that when you do a numeric limit and you're looking at like numbers that are really close to negative 1 on either side, that the numbers for the y values are definitely not close. This is negative 9, then we're jumping to positive 10 and positive 100, and so this doesn't behave particularly the same way that it has in the past. So we're going to go to a graph to kind of make sense of this. So y divided by 1 over x plus 1, again from the past and in pre-cal, we know it's rational. We know there is a vertical asymptote where the denominator is set equal to 0. And so we know by looking at it that the x equals -1 is going to be a vertical asymptote to this graph. And so I'm going to go over here to the coordinate plane and show that. Okay, so there's my vertical asymptote, and then we would choose numbers to the left of -1, like -2, for example, would be probably a good choice. 1 divided by -2 plus 1 is 1 divided by -1, which is -1. So -2, -1 is on the graph. If I use -3 here, that would give me a -2 on the bottom. So -3 would actually give me -1/2. And then kind of skipped ahead there, but there's no hole. I don't see anything that cancels from top to bottom. And also, this was the dA, but the horizontal asymptote, which I did skip over, so we're coming back to it. Horizontal asymptote can be found by comparing powers on the x from top to bottom. You've heard me say that a few times this year. So since the top has a x to the 0 power, if you will, the bottom has x to the first, power on top is smaller than bottom, then that means that the horizontal asymptote is actually going to be right on top of the x-axis, which is y equals 0. And so that way I can kind of predict what's happening with this picture with these points now. Change the color. Okay, so I know that in the third quadrant, this graph looks similar to that. And then going back, if my vertical asymptote's at -1, you might want to choose 0 and 1 as values for x. If I put 0 in here, that's 1 divided by 1, which is 1. So 0, 1 is on the graph. And then if I choose maybe a 1 and put it in for x, that's 1 divided by 2, so 1 and 1/2. And likewise, we know that the graph's getting closer to the asymptotes, and so that's a pretty good model for what's going on. Okay, so I modeled it graphically. I modeled this problem numerically on a small scale. Using more numbers would, of course, been better. And the question's asking me for a two-sided limit as x approaches -1. And so let's kind of, again, try to make sense of why these numbers were kind of all over the place. So we'll break this down into one-sided limits, which is one of our current topics that we're studying and learning. And we'll start with the right-sided limit. Same problem. We got the graph going on. We can probably, hopefully, make the call now. Find the limit of this problem as x approaches -1 from the right side. So we are going to come in, our eyes are traveling along the x-axis, coming in from the right side. The closer and closer we get to -1, ooh, I'm running into an asymptote there. But notice what the y's are doing. They're slowly increasing. That's just the curve and the nature of the graph. And the closer I get to -1, it's just the y continues to rise. And so it's going this direction. So it's like reaching positive infinity there. And then if you take a look at it from the left side, okay, from the left side you're coming in this direction, and the closer you are getting to -1, you're following along the path of the graph, and the y's are actually decreasing this time, and they're going to continue to decrease. So here's pretty much the breakup of this. If this is a one-side limit approaching on the right side, we know the graph is, as it gets closer to -1 on the x-axis, the y's are not going to be a finite number. It's actually just going to keep going and rising to positive infinity. On the left side, we notice the graph is reaching the asymptote, but it's going downward, so this answer would be a negative infinity limit. But the original question, again, was here. Well, what's the two-sided limit? Since the one-sided limits are different answers, then the final answer to this problem does not exist. Because that is the answer, now this makes way more sense because of the fact that the x values, even though I chose numbers close to x, the y's were jumping all over the place. And so if I'd have chosen some other x values, you'd have seen these numbers increasingly get larger. And on the opposite side, these numbers for y would have increasingly got smaller. And so that's why, obviously, that we can't really kind of make a prediction as to what's happening, so it does not exist. Okay, so that leads us to vertical asymptotes. And we know some stuff about this from pre-cal from last year. But vertical asymptote calculus definition, or more content, is if f of x approaches that's infinity or negative infinity, sorry about that, infinity or negative infinity as x approaches c from the left or the right. So if your graph is approaching positive or negative infinity as x approaches some number from the left side or the right side, we call the line x equals c a vertical asymptote. We call the line x equals c a vertical asymptote, which makes sense because we just saw that in the last picture. X equals negative 1 was a vertical asymptote. If the function f has a vertical asymptote at x equals c, then that just means that f is discontinuous at c. Vertical asymptotes occur when the denominator is equal to 0 and the numerator is not equal to 0 for the same value. And that's exactly what we just did on the last problem. So it's basically just tying all of this stuff together. Limits, approaching a value, and if you notice that the left side and the right side are approaching positive or negative infinity, then that's going to indicate there's a vertical asymptote in your graph. And at that vertical asymptote, there's a discontinuity. The graph is discontinuous. And we know from the past that vertical asymptotes occur when the denominator is equal to 0. Okay, so let's see. Determine if the following have vertical asymptotes and discontinuities. Just based on the last slide, f of x is equal to 1 divided by 4 times the quantity x minus 3. We're going to go with the vertical asymptote first. And so to do that, very easy. You're going to take the denominator and you're going to set it equal to 0. And when you do, you can divide by 4 if you want to. It's going to still be x minus 3 equals 0. And so that value is going to be 3. And so x equals 3 is going to be the vertical asymptote to that graph. Discontinuity is the place where the graph is interrupted. Well, if there's a vertical asymptote at x equals 3, then that clearly indicates that it is going to be discontinuous at that same location. And then kind of tying it back to things you've had in the past, discontinuities, there's two categories, removable or non-removable. This one would definitely be non-removable, but just because of the fact that it is an asymptote. Non-removable. Alright, let's move forward. Second example, g of x is equal to x squared plus 5 divided by x squared minus 4. We're going to take a look at the denominator again, kind of the same idea, and you notice this time it's a quadratic. Couple ways to solve a quadratic equation of this nature. You can either transpose and then do a square root, or you notice that it's a DOS problem possibly, and you can factor it. And that's totally up to you. It just depends on what you see first. But just show me how you thought about it. Alright, so I kind of started the factoring method. So I got x plus 2 and x minus 2. And that means that x plus 2, when it's set equal to 0, then the vertical asymptote is going to be x equals negative 2. When the second factor is set equal to 0, kind of picture that in my head, and I transpose, then x is going to be equal to positive 2. So in example 2, there are actually two vertical asymptotes, which means that there are two discontinuities in the graph. And likewise, they are non-removable. Again, tying it back to the limit, if I were to take this problem and do a limit as x approached 2, we'll say, from the left and from the right, you'll notice that the limits on both sides are reaching positive, negative infinity, like they're doing different things, and so that's why there is a discontinuity there, and a vertical asymptote for that matter. On number 3, just kind of speeding ahead here, this kind of is the same type of problem. However, I do notice the top, actually, let me write this down. The top does have a GCF, so I kind of need to show that. Let me backtrack here. Alright, so there's my top numerator. My bottom is going to be x plus 3 times x minus 3. And looks like my binomial factor, x minus 3, is going to cancel nicely for me. And so my new equation set up is going to be f of x is equal to 3 divided by x plus 3. And so just based on my new equation, my new simplified equation for example 3, I have a couple different things going on. I actually do have a hole in this one because I just canceled a factor with x. The hole again occurs whatever factor you canceled, you set it equal to 0, and you solve. So very easy. There is a hole at x is 3. And then when we want to try to find the vertical asymptote, we just kind of look at the bottom, take the denominator, set it equal to 0. And we got that part. And then also we could look at it with limits as well. Okay, so there's definitely a discontinuity at x equals negative 3 because there is a vertical asymptote there, which is non-removable. And the same thing for number 4. You would notice this is trinomial. You would factor it, and then you would factor the bottom in DOS form. 4 is going to be similar to number 3. And kind of work that out in your notes and see what you come up with. Okay. Alright, next we're going to look at the following limits using properties of infinite limits. So we'll start with number 1. Okay, another set to go over, but we'll do this first. So find the limit as x approaches 0 of 5. We've done this with properties of just basic limits before. So again, I need you to picture this as y equals 5 in your head. If it's y equals 5, then that means the graph is going to be a flat horizontal line. And when x is approaching 0 on both sides, because it's a two-side limit, then the height of that line is still going to be 5. That's a good way to see it in your head. Okay, on 1b, find the limit as x approaches 0 of 1 over x. Well, again, picture this as an equation. Y equals 1 over x, that's just a rational function. There's an asymptote right on top of the y-axis, and we know what the graph kind of looks like. So when we're looking at it this way, hopefully in our head. We're seeing this, and we're seeing this. Find the limit as x approaches 0. It is a two-side limit, so you're coming in both directions. Again, from the right side, the height of the graph is not going to actually reach a number. It's just going to keep extending up. So that would be like positive infinity. When you're approaching 0 from the left, the graph is going the opposite direction, and it's continually to decrease in a negative infinity direction. So this one does not have an answer. And it's similar to the first example we went over today. Okay, on C, find the limit as x approaches 0 of 5 plus 1 over x. And so what you can do basically is, I just took on purpose the same problem. So in part A, we did the limit of 5, we found the answer. Part B, we did the limit of 1 over x, we got an answer. And now for part C, I'm asking you to combine both parts A and B with this plus sign, find the sum, the limit of the sum. And so a really good way to think about this is just to split it up into both parts. Now we've already done the problem, so we should be able to see this. But if you had this as the beginning original problem, you would want to write it down like this. Kind of separate it into two problems. Okay. And then, so we already know this answer is 5, so we'll bring down our answer of 5 for that. Drop our plus sign down. Now, on the part B, I did it graphically, but we really could have just substituted as well. 1 divided by 0 is undefined. But remember my comment the other day, never, ever, ever write undefined for a limit. You have to use the beginning. You only write undefined when you're trying to give me an answer to a problem, a math problem that's not involving a limit. So in this case, it is does not exist for that part. So I really don't know what to say there. And then you're going to kind of put those together. Likewise, same deal with number 2. You can see like the limit as x approaches 0 of 4 is given to you here. Well, that answer would just be 4. And then find the limit as x approaches 0 of 1 over sine x. You would figure out what that answer is. And then look at C. I've taken the first problem and the second problem, and now I've multiplied them together. That's a property of infinite limits. And so once we find this answer and this answer, then we can kind of just multiply the two together. Okay, so you may want to do this in your calculator. Go ahead, grab your graphing calculator and go to y equals and type in 1 divided by sine x. And when you do so, you'll see an interesting graph like that alternates. And so if you're looking at it on your screen right now and you're looking for, well, what's the limit as x approaches 0, it kind of depends on which direction you're looking. Again, this is a two-side limit. If you are looking on the left side, let's say, coming in from the left, then the closer you get to 0, the graph is actually moving down to negative infinity. If you are coming in on the right side of 0 and approaching it from that direction, then the graph is moving upward. It's getting close to the asymptote, which is on top of the y-axis, and it's reaching positive infinity. And so like the book will have to be clear about what direction they want you to use, but this definitely doesn't exist if it's a two-side limit. And then you'll take the 4 on this problem, you'll write this and this, 4 times whatever this is. Okay, so I kind of left this hanging in this, so I want to clarify something. You'll write this when it's a two-side limit, but on these property problems, they're going to really, most likely they'll give you like the positive, like a right side or a left side. So for this purpose, let's say it did say a plus and you're coming in from the right side, then this graph is moving upward, and so that answer would be positive infinity. And so to complete part C, well, what's the limit as x approaches 0 from the right side of 4 times 1 divided by sine x? It is 4 times infinity, and infinity is obviously not a finite value, but if I quadruple it, it's still going to be infinity. So you kind of can think of it in those terms. Okay, like that. And back to this one, same deal. So let me be a little bit more specific. If I had said, come in on this graph right here, from the left, then we can see that this graph, the height of it is reaching negative infinity because it's not going to stop. So let's say I had that problem and I got negative infinity for that piece. Well, now I'm adding 5 to negative infinity. Well, it's still going to be negative infinity. It's just 5 more, okay? And so that's it. That's going to be more like what you'll have as practice problems. Okay, all right, so we're going to take a look at some of those practice questions in a textbook. Make sure on the properties that you do pay attention to like what side of the limit, and you can do that graphically using your graphing calculator as well. Okay, so again, the whole purpose to this is making sure you understand that infinite limits do exist. They are the calculus connection to vertical asymptotes, and you need to keep in mind that there's different ways to kind of see them, and you need to know all of them. Numeric approach, graphic approach, algebraic approach. I don't want you just practicing the calculus to assignment using pre-calc. I mean, I know I did here, and that's fine, and you can do that, but you also need to know the calculus as well. So you need to have both in your head. Okay, so we'll give it a try. Again, looking for infinite limits.